We'll just wait for a few minutes and then start. If you guys have any questions, feel free to ask me. Okay, I guess we can start. I'll recap what we covered last time. Yeah. Okay, so last time we saw a use case of typecasting with classes involved, especially okay, so starting with classes. So let's say I have two different classes A and B, and two objects instance of those two objects instance of each of these classes A and capital B. The objects themselves are small and small b. Now let's say you make pointers to them. So you take the object's address, okay, and put them in P and Q in with the appropriate data types. Okay. Now the question comes, can you switch them, right? Can you switch the actual objects? No, you can't. Again, the reason being there is no rule which relates these two classes. They can be like pretty much any generic class, right? So how does a class which has member variables integer and let's say another member variable double, they're essentially two different classes. How do they interact, right? So those two things being different are not so simple when you want to just typecast one to another, right? Whereas in other cases where you had um, inbuilt data types, you were able to convert one to the other, right? Okay. Pretty similarly, if you so this was being done implicitly, okay. So if you try to do it explicitly, also this does not make any difference. Again, there is a reason being that you are trying to uh, uh, you're trying to do the same thing, but it's just that you have written the syntax more explicitly. Doesn't make any difference though, because end of the day, it has to use some rule to convert one class to the other. And there as such exists no such rule which makes this same, right? Okay, right? Now, similarly goes, if you try to write A equals to B or B equals to A, okay? Um, Opposite of that, when you write A equals to um, using the typecasting explicitly, similarly for B. Now, we were able to write pointers, okay, before, right? So idea sort of carries forward here. You cannot write exchange pointers as such implicitly. While the address that P and Q store are of the same data type, in the sense they are both storing unsigned long integer, okay? But, and you can um, store one address in the other because there is no loss of data as such. That is absolutely correct. But the data they are both pointing to are different. So implicitly, that is not allowed to do. Because again, there is no um, it's like saying I mean one has to be definitely careful with pointers, especially when you're trying to implicitly cast, right? Because otherwise, how does it know how to point towards? Like it's pointing to something, yes. You can, technically speaking, treat the starting at the starting address. How do you want to treat data from that starting address and keep iterating, right? Those things you can explicitly saying you can do it and can be done. So hence the syntax works, which essentially just says the pointer that you have in Q, I'll treat it as class data type A. Similarly for P, I'm treating it as B. Okay. Now here comes the question. Even if you do it, do you actually are able to use them or not? Right. That's where you can try printing this stuff and then see what you're getting. Okay. So you'll actually get garbage answers. You can treat location of A as B and try to access the variable D. Okay. You can try to store you treat B as A and try to access I. Okay. Technically, it can be done because there is a rule which that class, when it is formed, is being used. Okay. But it does not mean anything for those objects, for the object of the other class. Okay. In certain cases, you might be accessing things from out of bounds, right? Okay, got it. Now, if we come to derived classes, we see that because derived classes inherit their parent class, they have the information of the parent class. Okay, so you can now play around with this. Let's say you write P and Q as those two objects. A equals to B, actually it gives an error. Okay, reason being, A, while it contains extra things, it has all the things of, sorry, while B contains extra things, it has all the contents of A anyway. Okay, so if you try to like treat the derived class as the parent class, you can technically access all the members the base class has, right? It's just that the data that you had, the extra data the class B had, are now not accessible because you are now treating them as A. But then again, this is like how much, what is contained in what? That's the one thing you have to think about. While promoting a data type from lower to high precision, okay, since the low data type is already contained in the, you can exactly represent in a high precision data type, then it is allowed and you're not actually losing any precision. Okay. In classes, that is slightly different way of thinking about it. Because the base class is already contained inside, like inherited in for the derived class, you can do the opposite, like while writing things, you can do it the opposite way. Reason being, you can access the derived class can access every member, sort of like it has a copy of all the members, whatever the base class has, right? So you can access those members, okay, like appropriately. These access specifiers will definitely be playing a role, but anyway, I guess you guys get the idea. Okay. Why not the opposite? Why can't you write base class as a derived class? Because base class does not have any information of the extra members that the derived class has. Okay. So hence this is the um, standard. The standard follows this format. Okay. But with the void pointers, you can always implicitly cast anything to void pointer. Okay. You can do it explicitly, true. But when dealing with pointers, it's always advisable to do explicit casting. Okay. So at least the intention is clear. Okay. Right. Next, yeah. So I hope this part is clear. Yeah. While trying to store a void pointer to any other data type, you have to do explicit casting. Okay. That's something you have to take care of. Can't do it implicitly, right? Coming to next example. So pretty similar to previous one where we had the values, the classes A and B. So B is the derived class. A is the uh, base class. Okay. Now you have this example. Okay. So now you're trying to access these variables separately, like trying to write one object into the other. So as in the derived class, let's say I write it to the data type of A, the base class, and then try to access these values. Okay. That's another example we took. Any questions so far? Okay. Right. I'll take another example. Okay, fast. Right. Recalling. Fast task. Recall. You had a original variable I and pointers and references to it. Okay, so those you can access this way. So you can access the reference, you can access the pointer. Okay, those things are fine. It's as simple as, okay, so I had I here, but okay, it's essentially like you can yeah, okay, you can dereference the pointer here and you just use ref here. That's fine. But what if you had constant references and constant pointer, sorry, and constant reference to the original variable I, which is what we have here. While trying to change the reference here, so that's what we try to do here. Trying to change the original variable, okay, through these references or pointers is not allowed because these are constants. Okay, so this is a recap. Now, to temporarily use these variables, but since the original is not constant, to remove the constantness of these variables, you can use a const casting. Okay, that's provided by the C++ library. So you can use const cast it to an integer reference for the reference guy, and then just write, let's say, some other value like 9 to it. Originally, it had 10. Very similarly, you can use the C style format where you use integer ampersand, so it's a reference, const ref as 9. Both achieve the same thing. For the pointer, you remember, you want to you use const cast to cast a pointer, and the temp inside this angular bracket template, you give it as integer pointer. So now your const pointer becomes an integer pointer. Now, because it's a pointer, you have to dereference it to access the value. So as a star. Very similarly, the const pointer, you are first casting it as integer pointer, then you are dereferencing it. Okay. All right. So keeping this in mind, okay, let's take more examples. Let's say I make a print function, which yeah, let's say it takes characters, string, okay, and I'll use the standard cout to just print the string. Okay, there is a null character ending, so cout actually knows where to end. So hence, because pass the whole string, it will print the whole character till it hits the null endpoint. Okay. Now, let's say I have the main function. I have a const character pointer, const yeah. Oh, sorry, that string. Okay. Can use the default hello world string. Yes. Then I can use print function. Okay. To let's say use this to print. Okay. Yeah. Okay. What do you guys think will happen? Okay. It'll throw an error. Reason being, I have a const character pointer and it accepts only character pointers, right? So again, this is an issue. One way you can resolve this, okay, is have overloaded, you overload the function, which is the print function, by changing its input parameters that it takes. Okay, so the inputs now become overloaded. So so the name is same, right? Okay, so you overload this const. Now let's say you want to print, it's all good. Okay, right? Now the reason you're able to do this is your print actually expects a const character, and I provided a definition for it. That's essentially the idea. Already I had a definition without the const, but if I add the const, cases where I pass the pointers, okay, if you just consider string here, that's a character pointer. If I define the const definitions also, along with the non-const definitions, I can take care of every use case, right? In general, that is okay if you want to just take care of it anyway. But sometimes you don't want to repeat the same code, because if you see the body does not change. Here it's a single line. But what if it was a huge code, okay? And sometimes you don't want to just repeat code unnecessarily. And let's say you just need to use the const version of it very sparingly. It could be like maybe once or twice, maybe, let's say. Okay. So in those cases, you actually can avoid defining the new function, okay, of this definition, right? And keep the same print, but now use const cast. Okay. So remember the syntax, const cast. Okay. Now we want to cast this current character, const character pointer to just character pointer, right? So just put character pointer. So we cast const constant string to character pointer. Okay, right? And then this complete thing is a new pointer now, which will get passed to string. Understand it? This is the C++ type. Okay, so remember with the original definition here, where I do not have const in the input parameter, which is a non-const character pointer like here, I had passed a const character, and that gave me an error, right, with compilation. Now, if I try to do this, it's all good. Okay. Reason being, even if the original is not like, if you think about it, here it's a string of array. Okay. Anyway, you will be using pointers to refer to the whole thing, right? So it being not const, again, it should be okay. In that sense, you can think that this way. Ideally, you should not be changing values like this, but as we know that here we're just printing the stuff, and we do not need to worry about it being non-const because we're not actually making any changes. It is safe to use this const cast, where you're temporarily not temporarily making it as not const. Okay. Similarly, you can use this C style way of doing things, where you cast it as character pointer. Okay. And you have sorry, const str. Okay, that's it. This is C style. Now if I just compile it and then yeah, that's all. That's what we expect. Okay. It prints in the same line because I do not end it with any end line or new line. Okay. So that's what we expect. Okay. Okay. Any questions so far? Right. Moving on. So let's take more example of this cost cast. As usual, I'll include the IO stream file. I have, let's say, a class A. I've defined the integer I. Okay. By default, this is private. Okay. Remember that. I'll make the constructor for this class. Okay. So remember the name of the class when used as a function name, like in this case. Okay. That's when you know it's the constructor. So it takes underscore I. Let me call it. That's fine. I'll call it as. And I want to use that to write my write the member I, which is part of this class. Okay. And I can just leave the body empty. I'll make another function, the get function. Okay, which is of const data type, where the return is I. It's essentially the getter function that we saw like much before. But essentially the idea is that because it has a member which is private. Okay. Yeah. So because the member is private, you should not be able to access this member outside the class. But let's say we want to still get the value of it, but without changing it. Okay. So you make the function as const. So it should not be able to change the any value it takes. Okay. So return is simple, but it's const, and anyway, it's not changing anything. So it's good practice to actually make it const so that you know the getter function is not going to change any value. Okay, that is the idea. Now the setter function, not so much because it will change values. So let's say takes the value j and sets I equals to j. Okay, simple, fair enough. Now we'll have the same void function of print. This takes character pointer, let's say str, and like before, we'll print with standard cout string. Okay, and this time I end the line. Okay, right. Now let's write the main function so that we can put all these pieces together. So make the const character. Let's say const str. Very small. Hello. Next, I have the print function, which takes const. Okay. Very similar to what we did in this case. So we'll take the const pointer. Okay. Sorry. String takes the const string, casts it into character pointer. Okay. Temporarily. So constness gets removed. Now print can happen smoothly. That's what we saw before. Okay. Right. Yeah. This just for completeness, I will say. Yeah, this will give you an error. Let's just run this quickly. So we're sure that everything is fine. Okay, all good. Now, let's say I define the object of A, okay, as const. Oh, and it has a constructor, so let me actually pass some value. Let's say 4. Okay. Now, let's use the getter function to get the values. value of I in A in N, right? Isn't it? So value of A is 4. So it's const, and the function is const, okay? Which means your function should not be changing any value. So that's the idea here, okay? And when your object is const, you should not be able to change its members. That is the idea. I'll repeat. When your function is const, the function should not be able to change any values, okay? Especially especially the inputs that you are giving, okay? So they don't change any values. Now, when your object itself, right, is const, it means that its member should not change. So getter function anyway does not change anything, right? And your object is also const. So all good, right? Okay.
Where is it necessary to define the getter function const?
Normally no, but it's like
But in this case, when the object is constant,
no,
I think it should error out or something.
you can try it. Uh, the thing is, the void function did not get marked as const, so this one get has type const A. I think I get why it is happening. Mm, Here, essentially, it is accessing the I through this pointer. Okay, I see. I see the. Okay. So it's accessing I through this pointer. Where is this? Yeah, which itself is defined as const because object A is const. So this pointer, while it is referring to the object A, okay, gets a constness also. The pointer itself also gets constness. That's what it's saying. Has type const A. Hmm. Okay. Function is
So
not
this
done.
question was in the assignment. I could not able to understand it fully. So if we do return star this,
Return.
set return pointer this pointer,
Okay.
then it's same as returning I.
No, because this pointer refers to the object's address. Okay, I'll write it here. So this pointer is equivalent to saying address of A. That's it. So when you dereference this, okay, you are getting A. That's it. So ideally here, if you think about it, the constness of A makes this pointer also const. So I guess it expects all the member functions to be const, but why does the void function does not need to be? Hmm, Let me quickly take a look. The- Okay, so the print function is fine. I have the getter function, which is okay. Yeah, maybe I'll get back to you guys. Why exactly? I mean, the idea here is that it does not change it, which is consistent with the fact that we define it to be const. Hence, uh, oh, I see. Because of the return type. Okay. Actually, that makes sense. Okay. So here, the how do I put it? Let's say I use return I, right? So which is a private member. Okay. Now it's trying to return I through this pointer, which is a const. Probably because of that, it expects the return also to be of, hence the return type to be const. That's why. Because this one does not have any return type, it does not need to return anything. It is not const. I think that's the only reason. Because the object is const that is defined here, if you use the getter function, it will return some value. That is the job of this getter function because we're returning a value. Now, important thing to remember, it is access when you're calling as dot get function, okay? The getter function gets called, but now the return type is decided by the return whatever returning, right? But the I here is being accessed. Okay, this is important. The I is being accessed through this pointer, which itself has the constness to it. Okay, so because of it, remember this way. You can think of it this way. So let's say you have a function of const integer, right? Let's say this way, and you're returning some value from, let's say, some other library or function 2. Okay, so this is some I and this is some j. Sorry, no, right? So let's say it takes the same value. Now, function 2, let's say it returns a constant, right? This is the value of function 2. If your function itself is also not respecting the data type, okay, same return data type, it will not work, right? This will throw errors. Okay, so the right way of thinking about it is, what is the data type that you're trying to return? Okay, that should be the data type of your function, because the function also will return whatever it return gives it, right? And here in this case, I is accessed through this pointer. Okay, and this pointer, remember, has the address of A, which is of const data type, where A is of const data type. So this pointer itself also becomes of constness, const qualified. Okay, so while it accesses I, it uses its const pointerness to access I, right? Hence the data type also, whatever you're trying to return, also needs to be of const. Yeah, my bad. Now I hope this is clear. Okay, the difference here and here is that you're not trying to return anything here. You're trying to set values and such. There is no return. So this value, it's we'll come to that while trying to access this. But now again, going by the same logic. Okay, I'll just comment this part.
So when we specify const after the function name, so it means the function is constant.
Yes.
And what if we made the return types also constant? This work?
Return time needs to be constant, because if it is the return, if the function is actually returning the same value, here I, in a way, whatever we are returning is of const value, like through the const pointer. So hence the const return data type. To respect that, we have to have const here. That is also necessary. Okay. Now, another thing, you try to access, let's say, not access, but let's just try to just overwrite it. So I'll have a dot, yeah, sorry for that. A dot set value. It had 4. Let me try to set it to 5. Okay. Now if I try to do this, I'll get an error. Reason being, I'm trying to change a value, okay, j, which is of rewriting the value I, but I itself we are accessing through what? This pointer, which is of const data type, right? So you cannot change the value. It is very similar to, if you think about it, it's actually similar to this situation where we are trying to change the value of, give me a second. Okay. Charger. So it's similar to this situation where we had defined a value and now we have a const pointer or a reference here, in this case, a const pointer to access that value. Okay. But we cannot directly, like here and here, we cannot directly change that value. And hence we're getting this error. Okay. So to mitigate this, again, the idea is similar. We're trying to access the value of I, but this is also important to remember. How does your program know to uh, access certain variable, right? It uses sort of, it essentially uses that objects, this pointer. That is what you can actually think about. So because of the constness of your object, there is a this pointer associated with the object always, that also becomes a generate this const. Okay. Again, you cannot change this pointer anyway, which is a different thing. Now, what it means is that whatever this pointer also is referring to, you cannot change them, because it's essentially behaving like a const pointer like this, where the value itself is changeable, because that I have not, if you see here, that I have not defined as const. So I is changeable. Okay, you can actually change the value of I, but not through a const pointer. Okay, I mean, not directly at least. That's what we did here. So this is hence throw an error. Okay. If I have cast, okay, I use the same idea. I change it to a const reference and make a, okay. I set 5 to it. Uh, Now it should be good to go. So we're temporarily, yeah. So let's move it here. So that prints the newest value. Have it in both cases. So we check that the actual value is actually changing. Right, good to go. Fine. So the first instance, it prints 4 because, sorry, it prints 4. So the constructor here sets I to be 4. Hence, when we use the get function, it prints 4. That's very easy. Now, to actually change values, so we cannot use set directly. I hope you guys understand why. Reason being, A sets values when you call set function. It tries to change I, but the access of I comes through this pointer, which is of const data type. And again, your object is also const. So that's sort of the idea. It's two ways of thinking about the same thing, but the idea is that your A cannot change its variables. Well, directly at least. Okay. So the set function is not allowed to set the value to j of its member I. Okay. So we use the const cast, change it to a reference. Okay, a reference, and give the input as the object, and then call the set function. Okay. Right. Right. Here I hope the idea is clear. Here the return data type is also of const nature, right? So hence, oh yeah, I don't think you can think of it this way also. It's the same argument, because A is const. The the return variables also need to be all const in sort of a sense. You can change them by temporarily changing the object's constness, Like not exactly changing. This will not be possible if your private variable itself was of const nature. Okay, but you're trying to access the member. Okay, sort of through a reference here, trying to access the member through a non-const manner. Okay, now set can actually change this value if I is temporarily treated as not const through a reference. That's sort of the idea I'm getting at. Okay, all right. So, any questions? So, okay, let's look at the another form of casting. So we had looked at different type castings, and const casting was an interesting one. So let's look at some very useful type of casting. We actually saw them before in these forms, but they were the C style way. Okay, C++ allows you to do the same thing, but more explicitly and more clearly. Let's look at those uh, variations. Let's define the main function. Okay. Let's define a long variable. Okay, so it will be L. Let's say this is a value 8. Now let me print L. Okay, so yeah, okay, it's this. Okay, all good. Print 8. Okay, fine. Now let's define a double t, which is it says 7.5. Another double variable says it's a pointer. Uh, Pointer to d. Okay, store the ampersand d. Right now, if you think about it, long has storage for 64-bit integers. Okay, double also takes 64-bit integers. Okay, fine. Now, can I do this then? Uh, uh, okay, think of it this way. Let's specifically go with pointer t. That I think is reasonable to say why you can't convert one to another. While the double pointer itself also, the double variable itself is also of 64 bits data type. It stores in floating point format, while long stores integers. Okay, so long here, it stores integers. You can typecast things, yes, true, but more specifically, let's focus on the pointer itself, not the data type of variable. Okay, yeah, just give me a second. Yeah. Yeah. Oh, okay. So I hope this is clear. So while D itself is also 64-bit data type, as in it has 64 bits. It stores floating point numbers. While long also, while being 64 bits, it stores integers. So conversion from one to another, we saw that before. Okay. But recall, if I define a pointer, okay, what is the size a pointer takes? The PTRD here, it's of unsigned long integer. Okay. So it is also integer. Yes, it's unsigned. And the largest size your system can represent, the largest integer. Okay. That is the size of your pointer. So the pointer's nature and the size is exactly what long is. Long here the long is. Okay. So this should also work, right? But if let's say one goes to compile this, one gets an error. Okay. Because there is a small tiny thing called the data type of pointer D. Okay. Which you are trying to like assign long to a double pointer. Again, implicitly, this is all not allowed. Okay. But you can actually use typecasting explicitly and not lose actually any data or information actually. So you can cast it to long, okay, ptrd. I'll just mention it. Error, and just comment this. Okay, it. So actually it prints here. So I should print it again. Sorry, my bad. Okay. The number that you see is actually the address in decimal form now. Okay. So if you try to print ptrd, yeah. So this is what you see in hex form. This is the value. Same value in decimal form is this guy. Okay, right. Now, this is what a sort of conversion that we did where let me do that. This is this time where the data, the very all the bits you had, okay, whatever bits you had in pointer D, exactly the same thing. Okay, if you just consider and convert to an unsigned long int, okay, they are the same. So re- that representation is of for pointer D, that is the address, right? And the address can be actually stored exactly in long, right? So as such, when you just take the bits you have in one data type in one variable and use that as is, like copy it in a way in another one. Okay, in those cases you use reinterpret fast. This is for like essentially for this exact line. Okay, but we are writing in the C++ syntax. So I'll show the syntax now. Okay, so reinterpret cast. Here we gave the long uh, data type. So that you pass inside template and then the variable. So PTR. So we are taking PTRD as the input, storing it in L. Essentially the same line, okay, but more explicitly mentioning that. So this is the L mention C++ file. You're explicitly mentioning that your variable PTRD has a certain sequence of bits. I'm going to take the same sequence, okay, and just interpret that uh, pointer, okay, that address, whatever it was pointing to, now as a long. That's it. That's what reinterpret cast does. It does not change anything with the bits. It does not touch the bits. It just treats them differently. It's like a different perspective. Okay, so now if you want to, you can print L. So let's do that here and comment this guy. Exactly the same thing we saw before. Okay, so L has 8, that is fine originally. Now PTRT, so that is the hex address because pointer by default will print in hex. And in L, same thing. We have not changed anything. So 8. After using the reinterpret cast, printing L gives you this number. Okay, right? Oh yeah, another thing you can. So this is the syntax for reinterpret cast. Okay, any questions? Uh, okay, I can print size of long, size of long like this. Okay, uh, this is just to check what I was claiming. You can do it this also. So size of long is of 8 bytes. Okay, size of long, not just long, double pointer. Okay, that is also of 8 bytes. Let's say we had without the pointer just double, then also 8 bytes. Okay, so this size of function is also very useful. What is the actual memory your data type is actually taking for this system? You can query it using the size of function. Okay, so this actually at least this should convince you that long is of 8 bytes. Okay, it actually takes has storage for 8 bytes. Double is also of 8 bytes. Double pointer is also of 8 bytes. Okay, so pointers themselves are also furthermore speaking, yet while this is of 8 bytes, the double itself, the data type interpreted, whatever the sequence of 32, 64 bits, that is interpreted in the floating point format. Okay, when you read a double, but when you have a pointer, it is an integer. It's just a number. Uh, More specifically, it's just an integer, right? And you should be able to store it inside long because that is also of the same data type. Implicitly, again, that's not allowed. You can do it explicitly. Okay. More specifically, you can use in C++ the reinterpret cast. You can do it the C way, right? But do understand why you want to use one um, format over the other. Okay. The reason being, here you are being more explicit as to what you want your pointer to convert into. Okay. So your pointer was a double pointer, right? You're taking the variable itself, right, and treating it as a long now. Okay, so it's the same bits which represented an integer are now treated again as an integer, right? So if you see the bit sequence of pointer d and long, they're exactly the same. There's no difference in between in those two. In those cases, you use rate-of-bit cast. Now, because pointers default behavior is when you try to print them here, their default behavior is to print the number, the 32-bit sequence in hex format. Okay, but long by default will print you in decimal format. So the same thing, because I'm printing long, okay, I'm getting it in decimal format. Okay, fine. Any questions? Okay. have the IO stream include. Right. Now, let's use the get back to the inbuilt int types. So this is a different perspective of doing the typecasting. We have, let's say, integer I, which is a value 7, long L, which is a value, let's say, 11, double the variable D, which is the value 3.14. Okay. Now, let's see out. I'll just print I to confirm. Static cast. Print 7. All good. Now, so what will this do if I write I equals to D? Okay, so we covered this before. This is implicit casting. Like you're converting a double to an integer. Okay, there will be lots of data. The decimals will go away. And one thing to remember here, if the integral part can be represented by the 32-bit integer format, it will get represented. Otherwise, whatever nearest thing, best thing it can do, it will do. Okay, just mention implicit casting. What was it? Typecasting. Simple. I can just do it explicit way also. Okay. Now, this is the implicit. It says there is no C or C++ here. This is the C style. I'll just call it C style explicit typecasting. Now let's look at doing the same thing in C++. Here we use this static casting method where convert into integer. Now input, which one? D. And what is the output? This whole thing, which gets stored in I. Straightforward syntax. Okay. And specifically, this will be C++ style. Okay. What just happened? We had used reinterpret cast here, and we're using something called static cast. What's the difference? That's the key thing you have to understand here. What static casting actually does is it will change the bit arrangement. So D had a structure of sequence, right, to represent 3.14. Now, if you think about it, whatever sequence of bits give you 3.14 in floating point format, that will be completely different with, sorry, this is 64-bit. So whatever 64-bit format was used to represent 3.14, okay, whatever is sequence, that will be completely different when representing a number called 3, okay, in 2's complement format, right? So static cast actually does that. It converts your variable to another data type, okay, and preserves the correctness of the values or going from one form to the other. It does not preserve, okay, what it does not preserve? It does not preserve the sequence of bits. because the sequence will change based on the value. So it keeps, you can think of this way, it tries to it keeps the values same or similar in the decimal format, not the bit format. While reinterpret cast keeps the bits same, okay, the two's binary format, okay, not the decimal format. So that way you can sort of try to distinguish between the two. Okay, that's what you saw when we printed pointer D and L. Okay, right. Okay, so let's print I. Oh, let's copy it. Let's print D also to get a more clear idea. So I is 7 is what you get here. But since we overwrote I with the integral value of D, so it prints 3. Okay, right? And D has not changed, so that's 3.14 still. Okay. Now, what if one does D equals to I? We're promoting a 32-bit integer to a 64-bit floating point number. Of course, this is allowed. Okay, and this is listed type casting, which is the same in both C and C++. Okay, and do the same thing. Basically, the opposite of this. You can do the same thing. Convert it to I, uh, convert it to a double explicitly, and then typecast I to D. Okay, so this is explicit typecasting. Okay, this time. Okay, it's very similar to this one, where you just specify what typecasting you're doing. In C++ format, this will look something like this. So you may use static cast, change it to double, okay, give the input as I, and here it will be explicit, yes, but C++ style. Typecast. Use the same format here. All right. Now let's print the value of D. We had done it for I, so let's not change it. Okay. I will make it endian. So inline and static cost. Yes. So 7 and oh, my bad. Okay, 7. That is not good. Yeah, okay. Yeah, it should. Yeah. So, yeah. Right. We expected this because these values are small enough to be represented exactly in a floating point format also. So 7 is still 7. Right. No change there. So let's have everything and then write it. I guess you can expect the result. It was 3.14. So D also now has 3. Okay. right? Any questions so far? I'll just reiterate what does it mean to use static cast and reinterpret cast. Static cast preserves the decimal value. You can think in that way. So if you want to try casting float to a double or integer to double float or whatever, all these combinations, will try to preserve the decimal value from one format to the other. Okay, that's what static cast does. While it may change the actual underlying sequence of bits in binary format, right? So that is the key takeaway here. That if you take reinterpret cast, it does not worry about the decimal representation of your number, but more on the actual sequence of bits. So if I take pointer D here and the same sequence of bits, okay, if I just treat it in a long format, I just say that, sorry, here it will be 64 bits. Yeah, sorry, maybe I did not anyway. So let's say it was 64 bits. Okay, I'll take the same 64-bit sequence, but now I will treat those same sequence in a new perspective, which is the rule of integers. Okay, because originally pointer D was of double pointer, but then again, well, it actually also stores 64-bit integer. That's true, but nonetheless, same thing. I'll treat the same sequence as now a long. Okay, that's what reinterpret cast does and write it to L. Right now, you can sort of think where this is going. If you want to actually cast pointers, reinterpret cast is actually quite useful in those cases. Let's say, yeah, let's say we have void pointers, right? So you can cast, let's say it is of some class data or user defined data type, a pointer, let's say some object obj. Okay, now you can pass object pointer to, let's say, store it in some void pointer R, pass that around in different libraries, and finally just reinterpret cast the same thing, okay, as a pointer. Now nothing actually changes because the original address now gets treated in this new format. Okay, we're taking the exact same address which was there originally, okay, in object pointer. You passed it around and you stored it in some word pointer. Okay, fine. The same thing, when you reinterpret it, you're essentially going to the same location now, right? But now, this time, instead of saying that it was a word pointer where I do not know how the data looks like, but because I know actually in uh, in my code that it actually looks like a star pointer, now I can typecast it, okay, and then start accessing its members, values, and functions, and so on and so forth. The good thing here is that the casting there, this is again just for understanding, you can obviously use C style ways, but being explicit is more important because you don't know if it might have done this casting in a static manner or a interpret manner. Here in this example, you will need an interpret cast because the sequence of bits that the pointer stores does not change. It represents the address, right? The only thing that changes is the way your variable that it is pointing to, right? So the pointer is pointing to some location, right? That location, how do we treat the starting address? Is it a double pointer? Is it an integer pointer or something else? Or a custom defined pointer? Okay, right? So in those cases, you can just use interpret cast. Static cast, when you want to actually question.
I have a question. So in
Yeah.
the previous one, during the reinterpret cast, so we cast the address of this pointer D to L. Now, if we do address of L and then dereference it, should it print 7.5, right? Because we are just reinterpreting that address to be address.
Now thing
stored
is
by L.
stored by L, right? So now L actually stores the address. You cannot dereference L because it's a variable.
Okay.
You can actually do one thing. You can define another pointer, double pointer, okay, or whatever. And okay, so double pointer PTRD has 7.5. So we need to actually use a double pointer now. Declare, let's say, double pointer temp or something, and write that temp as L, okay, using the reinterpret cast. But now we'll use the not long, but use the a one-to-one copy, right? I think it can work. We can just then you should try to refresh that temp, then you can get 7.5 again. Yeah. The I know it can get little confusing here. So PTRD itself was the pointer, yes, but L is not the pointer. Where is it? Yeah. L is just a long. We can't dereference that. Yeah.
Okay.
But the problem here is that when we try to print L, it prints the value, underlying value in the decimal format. That's the default behavior for long, integer, and so on and so forth, double and everything. So it has the same sequence as the PTRD, which is the unsigned address. But the address, when converted to a decimal format, will look like whatever we saw before. Yeah. But yeah, one can actually play around. We can explicitly write bits to one form or the other, but just one has to be careful. The reinterpret cast does not change the sequence of bits. That is important to remember, while static cast will. Right. In the question? We'll call it one. Right. So let's take another example. Now, let's say I have a variable 7. I've used this before. Why not? 19. Okay. And I have long L equal to, let's say, 12. And double D equals to 2.7. I can do one other thing. So these are the variables. I'll now make pointers out of them. So integer pointer ptr I equals to address of I. Then double pointer ptr d equals to address of d. Void pointer. Okay, so ptr d also I return. Now ptr with d, I can do either of these, right? No problem. This is implicitly allowed. Same thing. With d also. Oh, oh, sorry. Then I'll try to compile this and run. All good. No errors. But doing the same thing in the opposite direction. So ptr I goes to ptr d. Okay. Oh, sorry, d. And I'm trying to cast the pointer variable v here with I, right? I think you can guess what will happen. Error. Reason being, implicitly, it does not I mean, one can technically do it. And this what we'll be going to do, but implicitly it does not want to do this because yeah, again, a source of error. You have a void pointer. Now it just suddenly wants to become an integer pointer. That's a again a source of error. So it wants you to explicitly cast it so that you know that now yes, this is a pointer coming from this variable, which I'm trying to explicitly cast to a integer pointer, right? So same thing. If I try to do v equals to v 7, right? So just check that. That also throws an error. Okay. So this is this. Now let's do the same thing, but more explicitly. I have to use the integer pointer, okay, on pointer v, and then things will work. Oh, yes, sorry. Comment backwards. Right? Doesn't throw an error. So when you actually explicitly cast it, it's all good. Okay. So this is the system. Similarly, for pointer d, I can cast it as double pointer. Pointer v, so is also system. Both are valid. Okay. Now let's look at doing the same thing. Uh, uh, in the C++ way, I'll use static cast again. I'll treat it as a pointer. As the right. C++ type. Similarly for pointer d, cast double pointer. Okay. We can pointer d. Also C++ type. Okay. All right. So these are some of the examples I wanted to give today. Essentially, the idea is that you have static cast where the let's go to this one, where the data type of a variable, let's say it was double, you want to convert it into an integer. Okay. In that case, static cast is used. You want to explicitly say that I'm trying to change the I'm trying to change the value such that it respects going from one form to the other in the decimal format. In the sense, if I have a double, which will have, let's say, fractional parts, that will get dropped. Okay. And I get an integer. That's what I want. And trying to convert it to an integer means 29. Okay. So the type conversion here, it automatically takes care of it. Right? In reinterpret cast, you try to convert a sequence in the sense that you just read taking the same sequence, but now you're interpreting it in a different way. Okay, that's the reinterpret cast. Same sequence, but you use a different rule now to see to visualize the same bits in a different number format. Okay, that is this one. That is reinterpret cast. Const casting. That's what we saw just now. Essentially means you have object as input, and temporarily we are removing its consequence. We saw the various examples. You can take like use this feature, okay, to change the value of object where is defined as const, but inside the actual variable is not const. Okay, and yeah, you have access to getter and setter functions. So you use the setter function to change the value. Okay, in that case, you can use this const casting. Okay. Here, yeah, it was essentially trying to avoid duplication of code, where let's say the const version is going to get used very um, less number, like small number of times. So it's better to just maybe use the const casting so that you can use the not const um, definition and get away with this. Okay, right. Any questions? So yeah, it's all for right. So yeah, this is what I wanted to cover. So if you guys have any questions, you can feel free to ask, and else we'll meet next week. Yeah. So yeah, that's all for today. Yeah, I can cover dynamic casting. Nice. Yes. Yeah. Thank you. Thank you, everyone. Hope you guys enjoyed the class. Um, yeah, again, all with all these examples, it's good to practice. So take examples, write code, and play around with those functions. And yeah, see for yourself what's the input you're expecting and what's the input you're actually getting. And if there are any actual compilation errors or any other runtime errors and yeah, all those things. Yeah. Okay. Thank you. Thank you.